All right. Good morning. Woo, sorry. Um, we need to finish the activity we did yesterday. If you remember, we had started talking about Kepler's laws, which is all about how planets orbit. All right, how orbits work. And you guys already have learned that, like our Earth, we rotate and we revolve. So now we're focusing on how things revolve. And we got to the first of Kepler's laws. So if you haven't yet, go to functions formations of other celestial bodies. All right. And you're going to click on this Kepler's laws Google site. All right. You've already started it, so we just need to finish it. When you click on this, it'll look like this when it pops up right there. Boom. And you're going to want to click on this link so we have the site already up and ready to go. There she be. All right, we already did our prior knowledge questions, so we're down to Kepler's first law, which we already answered. We said that Kepler's first law is talking about the shape of an orbit, which is always an ellipse. All right, so that is what we started talking about. We talked about that an ellipse is a circle that's been flattened, and the way that we measure how flat an ellipse is by looking at its eccentricity, which if it's a perfect circle, it'll be 0. And then the more squished it gets, the closer that number gets to 1. All right, 1 is like a flat line. You'll never see a planet with that. Remember, comets are really, really eccentric and really flattened. Their orbits are. So Earth is at about 0.017. So it's kind of close to this, where it looks almost like a perfect circle, but it's not perfect. Okay. So then we start moving on to Kepler's second law, which is talking about the way an object's speed varies along its orbit. So if we look at this, let me go ahead and click to where we need to be, which is right about here. All right, it says Kepler's second law describes the way an object's speed varies along its orbit. So if we watch this, it's going kind of slow. And then when it gets close to the thing that it's going around, it kind of like zooms around. So a planet's orbital speed changes depending on how far the planet is from the sun. The closer it is to the sun, or in this example, the Earth, the stronger the sun's gravitational pull on it and the faster it moves. It's kind of like if you've ever gone to a roller skating rink and you hold hands with your friends, you go around the turn and you whip them around. That's what's happening right here, okay? So let's draw what's happening. Add information to the ellipse below. I'm going to make a circle. So this one I'm going to say is our sun. I'm going to color it yellow. Then I'm going to Control-C, Control-V. We need our other focus point. Remember, ellipses have 2 foci. I'm going to make it black because it's just space. At least that's what you can see here. The other point would be over here. It's just space. And then I'm going to make a teeny tiny planet. You can put it anywhere. All right. And what we notice, oh man, I want that guy to be blue, like Earth. Make sure to label where the planet or satellite will be moving faster and slower. So let's get a text box over here. Further away from the sun, it's going to be slower because there's less gravity out here whipping it around. And then over here, it's going to be faster. So as it moves around, it's going to whip around, and then it slows down out here. All right, and then I'm going to delete this so that it's just our image we're looking at. Save. Boom. All right. Look at the image where the eccentricity is 0 and describe the shape of its orbit created. So now we're going to go scroll down a little bit. Here, eccentricity is 0. And what is that shape? Say it with me. It's a circle. It's a perfect circle. So when eccentricity is 0, the shape is a perfect circle. Boom. Is the speed of the planet constant, or does the speed increase at certain spots? So let's look. There it goes around in a circle. Circle, circle. Looks like its speed is not changing. All right, because its distance from whatever it's going around doesn't change. So the speed of a planet that would move in a perfect circle is constant. It stays the same. All right, so now we're going to look at 0.8. And 0.8, remember, is really close to 1. So it's very ovally shaped or elliptical. So when eccentricity of an orbit is at 0.8, it is very elliptical, oval. All right. So is the speed of the planet constant, or does it increase at certain spots? So there she be. I'm going along, just carrying on, traveling along, getting closer to the sun that it's orbiting around. Speed goes definitely faster. All right, and you can see that in this too, or more so here. Look at this whip around. All right, so the speed for an elliptical orbit for a planet in an elliptical orbit will increase around the sun. So we're going to double click the drawing to the right and move the 2 red arrows to where the planet moves the most quickly and slowest. Double click. The fastest would be right here, right? Boom. And the slowest would be way out here, the furthest point from the sun. Save. You got it. All right, finish the sentence about Kepler's second law. As a planet moves closer to its star in its orbit, what do we know about its speed? It will speed up. How I want to say it. So a planet moves closer to its star in its orbit, its speed will increase. That's more technical sounding. All right. So the third law, here we go. Boop, boop, boop. Let's move this guy to right here. Kepler's third law, it is comparing the motion of objects in orbits of different sizes. So the third law describes, where's memory? The motion of objects in orbits of different sizes. The motion of objects in orbits of different sizes. Boom. All right, highlight the word choice for Kepler's third law. I think you guys, this is like common sense, right? So an object that is further from the sun will take, is it longer or shorter, time to lap around the sun than an object that's closer to the sun. So a planet further from the sun not only has a longer path than the closer planet, but it also travels slower because the sun's gravitational pull is weaker out here. Therefore, the larger a planet's orbit, the longer the planet takes to complete it. So it'll be longer. Boop. You don't have to do this. I'm just going to, All right. Explain 2 reasons to support the statement above. It gives it down here. A planet further from sun not only has a longer path than the closer planet, so it has a planet further away has a longer path to travel. And then also, but it also travels slower because the sun gravitational pull is weaker. A planet further away travels slower because gravitational pull is up because the gravitational pull from its star is weaker. All right, watch the planets move around the star. Place a square over the planet that has the shortest year. So, which one of these is going to be shortest? I like this image. Which one's going to be shortest? Which one's going to be longest? All right, so what am I doing? A square over the planet that has the shortest year. So that would be closest to the sun. Shortest year. Again, these things are common sense. It's like if you are a runner in track, you know you want the inside lane because you're going to have less distance to go. Whereas if you're on the outside, ooh, you're going to have a longer, oh wait, save and close. What's the other shape? And then a triangle over the planet that will have the longest year. Triangle. Boop. Shapes. There's a triangle. And we want the furthest out orbit. Boom. I'm going to make that purple because I like it. Save. All right. Once you are done, push submit.